Hello, we're going to look at irrational functions. Most of this should be review, so I'm going to go through it a little bit quickly. So we have a rational function of the form of 1 over x, the most basic parent function we have. If we put 1 in, x equals 1, y equals 1. When x equals negative 1, y equals negative 1. And as x gets very large, this equation will keep getting closer to the x-axis but never touch it. And same thing if x gets very small. And as x gets really close to 0, this is going to get bigger like this, and from this direction and from this direction here. So that gives us a domain of x such that x not equal to 0, because we can't divide by 0. And that also gives us our vertical asymptote. And asymptote is something that a function equation approaches but never actually touches it. So we have a vertical asymptote at x equals 0, and the range is y such that y is not equal to 0, and that gives us a horizontal asymptote at y equals 0. So most rational functions will have two asymptotes, but not always. So let's look at a more complicated problem is when we have something that looks kind of like this, right? So the first part is I can find my horizontal asymptote by always taking I know the denominator can never be 0, so I'll go cx plus d equals 0, and I can do a quick solve and say that x equal to negative d over c, right? And you can use this formula right here if it's in this form, two basic linear equations, and you can always use that to find, use this equation and use these numbers to find out what this is the vertical asymptote, but it's also, helps you find whatever the domain is. You could use the formula, or you could just always solve. Now, for the horizontal asymptote, we're going to find that by doing this, multiplying the top and bottom by 1 over x, and that leaves us a plus b over x all over c plus d over x. Now the concept is we're going to look at what happens as x approaches plus or minus infinity. Well, just like up here, as x got very large, it got closer and closer to the x-axis, or closer and closer to a value of 0. And that's what's going to happen here. It wouldn't matter what this value of b is. As this gets really large, this becomes 0, and so does this. So what is our y value going to be equal to as x gets very, very large or small? It's just going to be a over c. So what does that mean? We have a horizontal asymptote at a over c. And that will always happen. It also gives you a range. Our range is going to be any value. It can be any value except for this value, right? It's never going to actually get there, but that is our horizontal asymptote. So you can use this equation of this form. If it's two basic linear equations, you can always find the horizontal asymptote that way when they have the same, and for anything with the same power. So it's x squared, it's this over this, cubes to the 4th power as long as they're the same, and so on. Sound good? And something different happens when they're different, but we'll see that later. So let's go ahead and look at an example, and let's look at example 7, right? So example 7 says determine the domain and range of the function y is equal to 1 over 1 minus 2x. Confirm your solution graphically. So the first thing I'll do is find my domain. I know that that has to be equal to 0. You can use the formula that we just derived, but I just like solving it. It's just easier for me. So x is equal to 1/2. So that means my domain is x such that x not equal to 1/2. And this is my vertical asymptote, right? Now, as far as the horizontal asymptote, well, I can restructure this and say 0 times x plus 1 over 1 minus 2x, and I can see that my using the property that we just talked about, that guy over that guy, is just going to be y is equal to 0, so our range is going to be y such that y not equal to 0. And this is my horizontal asymptote. That's my vertical asymptote. Now I can go ahead and graph this now and go I know I have a vertical asymptote at a half, and the horizontal asymptote is just the y-axis. And then I could plug some values in. When I plug 0 into here, I just get 1. So I know this is the asymptote here, so I know it's going to look like this. And then you get close to this line right here, something like that. And then I'll find another value to the right of the vertical asymptote, and I'll plug in 1. If I plug 1 in, I'm going to get -1. And now I can see it's going to get close to this one and go like that. Sound good? Good. So that's example 7. Let's look at another example. Example 8. And it says determine the domain and range of the function y is equal to 1 minus 3x over 2x minus 1, and confirm your answer graphically. So just like I did before, I'm going to go 2x minus 1 equals 0, so x has to be equal to a half. So that's my vertical asymptote, and then my domain is going to be x such that x is not equal to a half, right? And same difference, I can go ahead and find my horizontal asymptote by taking -3 over 2. And then my range is going to be y such that y not equal to a -3 halves. So now I know my domain, my range, and my vertical and horizontal asymptotes. And now I can use that to graph it. And I can, well, the first one is at a half again, so I have a vertical asymptote here. And the next one is at 3/2, so that's -1.5. Good. So I have the asymptotes, and then I'll plug in 0 is an easy number to plug in, and I get -1. And now you can see it has to go through this right here, so I can go through here, and something like that. It's not perfect. And then I'll plug in 1 to get the other one. Well, if I plug in 1 up there, I get 1 minus 3 over 2 minus 1 is -2 over 1. It's -2, so at 1 it's -2. And you can see that's going to be there, so I know it's going to look something like that. And there you go. So I used knew how to find vertical and horizontal asymptote, plug in a few points, see what's going on, and then I could sketch the graph accurately. Sounds good.